All right, today we are going to talk about curves defined by parametric equations. This section is actually pretty fun, so get ready. I think you'll actually enjoy this. I know that sounds silly, but it's true. So here we have this image on the left, and it's a real loopy curve. It goes all over the place. So imagine that a particle moves along this curve, C. It's impossible to describe C by an equation in the form of f of x because C fails the vertical line test. And we know that if we were to draw a vertical line through the curve C, it would definitely fail. So it doesn't seem like a function. But, and here's the neat part, the x and y coordinates of the particle are functions of time. And so we can write x as f of t and the y as g of t. Such a pair of equations is often a convenient way of describing a curve, and it gives rise to the following definition. Suppose that x and y are both given as functions of a third variable, t. This t is called a parameter. So suppose that x and y are both given as functions of a third variable t, and they're given by the equations x equals f of t and y equals g of t. These, because they're in that third variable, these two equations are called parametric equations. So these are parametric equations. Each value of t determines a point, xy, which we can plot in a coordinate plane. As t varies, the point x and y is actually f of t, g of t, and it varies and traces out a curve C, which we call a parametric curve. So this curve up here that we saw in the beginning could be mapped out using these two parametric equations, f of t and g of t, and they would create the ordered pair that we would plot, and the curve that results is a parametric equation, or a parametric curve, excuse me. The parameter t does not necessarily have to represent time, and in fact we could use a letter other than t for the parameter, but in many applications of parametric curves, t does denote time, and therefore we can interpret it as the ordered pair xy is f of t, g of t, as a position of the particle at time t. So what we're going to do in this section is learn how to sketch a lot of these curves and then to take these two parametric equations and put them into terms of x and y. And so we'll make a lot of relationships here. So let's take a look at example 1. This is asking us to sketch and identify the curve defined by the parametric equations x equals t squared minus 2t and y equals t plus 1. So to do this by hand, what you would need to do is create a table, and in this table we're going to have our t values on the left, our x values, and our y values on the right. The x values come from the equation t squared minus 2t. So for this first table, I'm writing out how I'm getting the x values at the top, just to make it really clear for you. The y values come from the equation t plus 1, which I also wrote out at the top. So because we're not being told what values of t to use, we're just going to choose a few to see if we can get a nice sketch of this curve. So I'm going to choose the values -2, -1, 0, 1, 2, 3, and 4. So, just like we would in any table of values, you're going to take the value that you have on the left and plug it in to find the value that you're looking for. So we're going to take the value of -2 and plug it in for t in the x equation. So t squared would be -2 squared, which would be 4. And then we have -2 times a -2. That would be +4, so we'd have 4 plus 4, which would give us the value of 8. So all I'm doing is taking the t value and plugging it into the x equation to get the x variable, and I'll do the same for the y equation. So -2 would go in for t in the y equation, so that would be, instead of t plus 1, it would it would be -2 plus 1, and -2 plus 1 is -1. So as you can see, we're just evaluating in the equation for x and in the equation for y. So let's choose another one. Let's say I chose the value of 1. 1 squared is 1, minus 2 times 1 would give me an x value of -1. And if I'm looking for the y value and plugging it in for t, 1 plus 1 would be 2. So go ahead and pause your video and complete filling out this table for both the x's and the y's. So hopefully you're able to finish filling out your table, and what you've actually done is you've taken these two parametric equations, x and y, and you've evaluated them at various t's. And by doing this, you're actually creating ordered pairs. So the x value is going to be the x value of your ordered pair, and the y value will be the y value of your ordered pair. And we can now plot these ordered pairs on a coordinate plane. So to create your coordinate plane, you want to look to see the type of x values that you have and the type of y values that you have. So it looks like my x values are pretty much ranging from -1 to 8, and my y values go from -1 to 5. So you want to make sure to create a coordinate plane that will cover those numbers. So here we have a coordinate plane that we're going to plot the ordered pairs on there. And as you plot the ordered pairs on there, try to mark the t value for each of the points. So for example, the first one is 8, -1. So here's 8, -1. And that is for t equal to -2. And then we have the point 30, and that is for t equals -1. Then we have the point 0, 1 for t equals 0, and -1, 2 for t equals 1. And you just kind of keep going, plotting all of the points as best you can. And as you finish it up, this should start to look like a familiar shape. So it looks to me like this is a parabola that is laying on its side. And so this set of parametric equations made a lovely parabola. Now, because we're talking about this in terms of t values, okay, so t equals -2, -1, 0, 1, 2, 3, and 4 is what we plotted, we should try to show the direction in which this graph is essentially flowing. So from -2, it moves up, and so it's kind of flowing. If we were to talk about its path, this is the path that it's taking for the variables that we've plotted. So again, this looks like a parabola. And we definitely showed the flow of the graph by using these arrows. So if we were talking about a particle moving along the curve, a particle whose position is given by parametric equations moves along the curve in the direction of the arrows as t increases, which is why we drew the arrows in the prior graph. So it shows that if there was a particle moving, the direction in which it's moving is shown by the arrows. Notice that the consecutive points marked on the curve appear at equal time intervals, but not equal distances. That is because the particle slows down and speeds up as t increases. So these may be at t equals -2, -1, so each 1 unit apart, but notice there's much more space between these 2 points than these two, and as the curve flows, it changes, and that's just because of the way it's moving, speeds up and slows down. Now, if we wanted to confirm that this was a parabola and put this parametric equation in terms of x and y, we can do that. So we're going to do what's called eliminating the parameter. And so basically what we're going to do is force this onto a Cartesian plane or a Cartesian xy idea and force it into the xy axis. So we have our original two parametric equations as x equals t squared minus 2t and y equals t plus 1. Okay, so the easier one to solve is to solve this second equation for t equals 1, or for t, by subtracting the 1. And it's the easier one because it's a simple linear one. This top one would be, not as easy to solve since we have a t squared and a t, right? So you might not even be able to do so. There are times when you're going to have just a t squared, and you need to be careful. Let's say the second term wasn't there. You need to be careful because when you take the square root of something, remember there's a positive and negative. And I'll bring this idea back in a little bit, but I did just want to touch on that. So you want to try and choose the equation that's more simple. So if I were to solve this one for t, I would be subtracting 1, so it would be y minus 1. And I'm going to take that y minus 1, and I'm going to plug it in for the t in the top equation. So basically we're using the idea of substitution. So x is equal to our expression squared minus 2 times our expression. And the expression, remember, is y minus 1. So if I were to simplify this and FOIL out this first part, y squared minus 2y plus 1, and then distribute the negative 2y plus 2, combine our like terms, we get y squared minus 4y plus 3. We can see that this is, in fact, a parabola. So it confirms what we discovered using our graphing techniques. This parabola is just in terms of y, so our parabola is tipped on its side, and that's exactly what we saw using our parametric equation graphing techniques. Okay, so no restriction was placed on the parameter t in example 1. Notice we didn't have any specific t values that we were supposed to use. There wasn't any specific range of values, so we just chose some for our table. So we just assumed that t could be any real number, but sometimes there will be a restriction to t, and it will lie on a finite interval. For instance, the parametric curve x equals t squared minus 2t and y equals t plus 1. If we were to, same graph that we had above, but if we were to restrict the x values, or excuse me, the t values that we were allowed to graph, we wouldn't have the full parabola. We would just kind of have this sort of upside down Nike swoosh shape here. So shown to the right is the part of the parabola that would be there, and it would be from 0, 1 all the way to 8, 5. So the arrow again is depicting the direction in which the curve is flowing, and so it's going up and then switches up and to the right. Okay, so in general, the curve with parametric equations x equals f of t and y equals g of t is going to have some sort of interval, and so that means it will have an initial point, which means when you take your parametric equations and evaluate them at that first number in the interval, that's going to be the initial point, f of a and g of a, and it will also have a terminal point, which would be the evaluation of the parametric equations at the end of the interval, in this case b. So the terminal point would be f of b, g of b. So let's see an example of that with a second sketch. Now we have an interval from -2 to 2. So first we're going to sketch and identify the curve, and then we'll talk about getting it in terms of the Cartesian equation. So here's our table of values. I put the interval on the left for t. It's ranging from -2 to 2, and I just chose to do the evaluations as a difference of one interval, so -2, -1, 0, 1, and 2. And then for our x and y values, we're going to evaluate using these t's for each of our parametric equations. So again, you're going to need to pay attention to your parametric equations to determine what your x and y values are. So at this time, go ahead and pause the graph and evaluate your parametric equations x equals and y equals for the given t values in the table. Okay, so hopefully you're able to evaluate using the t values provided from the interval for your x values and y values. And so now we're going to be able to graph this parametric or this set of parametric equations on the coordinate plane. So we're going to make a graph or a coordinate plane that will cover these x and y values. So it looks like my x values range from -3 to 3, so I need to make sure that my coordinate plane that I draw uses these values, and my y values from -4 to 0. So we're going to be pretty equal width along the horizontal axis, but we're going to need more of the negative numbers for our vertical axis. So now that I have my coordinate plane drawn, we can plot the ordered pairs. The first one that we're going to plot is -3, -4. So -3, -4 will be the first. Remember, that's my initial point because that was the first t value in the interval given, and this is the ordered pair that resulted from that t value. So this is going to actually be my starting point. So I don't want to draw, when I actually connect the points, I don't want to draw anything beyond this point. This should truly be where it starts, and then my terminal point will be the ordered pair that resulted from the last part of the interval, which was 2. So the ordered pair 3, 0 will be my terminal point. So you don't want to draw, and have your graph keep going because that would show more to our picture than what we actually want. Okay, so here's our graph. So notice I'm not drawing beyond those points. I'm going to connect them. Okay, I'm also going to label them as t equals -2, t equals -1, t equals 0, t equals 1, and t equals 2. And from that, I should now be able to draw the arrows to show the direction in which it's flowing or which it's moving, if a particle were moving along this curve. So there's my parametric equation. Notice I have my start here and my end up here. So my initial point and my terminal point. And I've labeled it with my arrows and with my t values. So now let's try and find the Cartesian equation that goes along with this. For this, we have the first parametric equation as x equals 1 minus t squared. And we have our second parametric equation as y equals t minus 2. And so with this, you want to try and choose the easier one to solve. So that would be the second equation. This is actually a good one to talk about that idea that I mentioned earlier about the square root. If I were to do the first equation and try and solve this for t, I would get x minus 1, and I would need to take the square root of that. So my equation would be t equals the root of x minus 1. The problem with that is when you take the square of both sides, you're going to have a plus or a minus, and you want to try to avoid that as much as possible because that can actually have a conflict with your domain. So when you're trying to find your domain later, which I'll show you shortly, this plus minus can actually have an issue there. So you want to try to avoid solving with square roots if you can. If you have something cubed, that's fine because cubed doesn't have to deal with that plus minus idea, just the square roots or something to the even exponent. Okay, so let's go ahead and solve this second equation for t. So that would be y plus 2 is equal to t. And so we're going to use this y plus 2 expression and we're going to plug it in for t in my x equation. So here we have x is equal to 1 minus quantity y plus 2 squared. And if we were to simplify that, we'd get 1 minus y squared plus 4y plus 4. And then we can distribute our negative and combine like terms to get negative y squared minus 4y minus 3. So this would be our Cartesian equation. Now, because this because this situation had an interval to begin with, we need to create a new interval in terms of x and y. So we're going to use these equations to help us do that. The interval that we started with was from -2 to 2. And so what we're going to do is actually use this equation that we solved for t and plug that in for the t in this interval. And we're going to just have to solve a compound inequality. So we'll have -2 is less than or equal to y plus 2. So we're replacing t with the expression for what it's equal to. And notice now we have a compound inequality that needs to be solved. So you're just going to minus 2 on each side. So my resulting interval should be from -4 to 0. So whenever you start with an interval in parametric form, you need, and you're writing it in Cartesian equations, you need to have an interval for that as well. So here's example 4, and it's saying what curve is represented by the following parametric equations. So of course, you know, we're going to throw in a little bit of trig here, but it's going to follow the same exact process of what we did before. You're still going to create a table of values so that you can evaluate using various t's for your x and y to get your coordinate points, and then you'll still graph them on the coordinate plane. So let's set up the table to start. So here's my table of values, and I figured I'd set this one up with you since we're going from 0 to pi over 2. So remember, you want to start your table with 0 and end it with pi over 2 since they are giving us that interval. Now this is in the first quadrant of the unit circle, so we need to think about what angles we know the sine and cosecant for. So that would be angles like pi over 6, so that would be something we could use, pi over 4, and pi over 3. So you want to kind of keep it to things when you're doing it by hand that are probably a little easier to work with. Now that we know what our t values are, we're going to take these t values, and I would suggest evaluating for the x first, since that's just the sine function, and then we can worry about the cosecant in just a moment. So the sine at 0 is 0. The sine at pi over 6 is 1 over 2. The sine at pi over 4 is square root of 2 over 2. The sine at pi over 3 is square root of 3 over 2. And the sine at pi over 2 is 1. So this is giving us good practice in our unit circle. Now, just as a little hint, remember that the sine function is our first one here, and cosecant is, is the inverse, not the inverse, but the flip, the reciprocal of our sine. So all we have to do for our y's here is to essentially flip them upside down, right? So starting at pi over 2, the flip of 1 is just 1. The flip of root 3 over 2, or the reciprocal, would be 2 over root 3. The reciprocal of this would be 2 over root 2. The reciprocal of this would be 2. And then I left this one for last, of course, since we have a 0 here. So the reciprocal of this would be 1 over 0, which, of course, you can't divide by 0. So this is really just undefined. Okay, so now that we have our table of values, we're going to need to plot them. So I'm going to create a coordinate plane here. I'm dealing with all positive type of values, so I'm going to keep it to the first coordinate. Now, something I should have mentioned before, because my x is defined but my y is not, the actual interval here is slightly mistaken. So we actually need to fix this, and I should have fixed it before. This should be just a less than, because we can't include 0 since for the one variable y, it would be undefined. So this should really just be a less than sign. Okay, so let's see if we can plot these points. So the first one, I'm going to maybe start with my pi over 2, my 1, 1, because I think that's probably the easiest to start with. And then my second one would be square root of 3 over 2 and 2 over root 3. And since I can't think of what those are off the top of my head, I'm going to use the calculator to help me get a decimal approximation for those. So that's what I would suggest you do as well. So square root of 3 over root 2, whoops, or excuse me, over 2 is 0.866, and then I would have 2 divided by the square root of 3. So my next ordered pair is going to be 0.866, 1.155. And now that I've plotted that point, I can do the same process for the root 2 over 2 and 2 over root 2 to get that decimal approximation, and then the other should be relatively easy. So I'm going to plot the pi over 4 and pi over 6, and then we'll talk about the 0. And as you can see, by plotting these points here, we're starting to get this nice curve. Now this last one is going to be, as it's approaching 0, we're getting undefined. So we're going to have that nice vertical asymptote there. Whoop, trying to hit all my points. And it's just going to kind of continue up in that direction. So notice I'm not extending it out in the forward direction because my largest t value is pi over 2. So my terminal point here is really 1, 1. So this is really the end of this. It's kind of hard to write the start of it since we have that asymptote there. But you can label your points. So this would be at t equals pi over 2, t equals pi over 3, t equals pi over 4, and t equals pi over 6. So that kind of helps us see our t values. And from that, you can kind of get the flow that we're kind of coming down towards our end terminal point. Now let's look and try to determine the Cartesian equation for this. So we started with x equals the sine of t and y equals the cosecant of t. And the relationship I know between these two is that the cosecant of t is equal to the reciprocal of our sine. So once I set up this relationship, I can very easily just replace them with their appropriate variables. So cosecant is y, and sine is x. So this would be a nice Cartesian equation for this situation. Again, we were given an interval. Our interval was from 0 to pi over 2. So we need to create a new interval to match that. So here's our interval. We started from 0 and we went to pi over 2. We know that we can use one of these equations to help me figure out what t is. I think the easier one is to use the sine. And if we start with x equals the sine of t, then we can undo the sine by taking the arc sine. So we can say the arc sine of x is equal to t. So that's what we're going to replace t with in this interval. So we'll go from 0 to the arc sine of x to pi over 2. Now we really need to get this in terms of just x. Even though there is x in this interval, we'd like to get it just in terms of x. So how do you undo the arc sine? You can take the sine of all things. So we're going to undo it. But if you do it to one, you must do it to all because we have a nice compound here. So the sine of 0 is what this is saying. This is saying the sine of the arc sine of x, and then the sine of pi over 2. So we just need to simplify this. Now the sine of 0 is 0. The sine of the arc sine of x is x. And the sine of pi over 2 is 1. So here's our new interval for this given situation. What I'd like to do now is show you how you can use your calculator to graph parametric equations. We actually briefly touched on this when we were talking about the revolutions around a curve when we were trying to graph things in terms of y. So now we're going to use our calculator to actually get that formal, how do you graph parametric equations? So to begin, the first thing you need is you need to go to mode, make sure you're in radians number 1, and then you need to arrow down to where it says functions. We're not graphing things in terms of functions anymore, we're doing it in terms of parametric, P-A-R. So we're going to hit enter there, and that will change the mode of our calculator. Now we can go to y equals, and as you can see, we have a totally different look to our y equals. Now I currently have my plot on, so I need to turn that off, and I'll go back to my equation. Now, for x1, I'm just going to type in t squared minus 2t, and when you hit the variable, t will automatically come up now. So t squared minus 2t, and then for my y, it was t plus 1. So variable plus 1. Okay, so now that I have that, I'm going to need to likely adjust my window, and I need to think to myself, what type of values was I working with? So I'm going to look back at the table here, and remember my x and y values are what we were really focusing in when we were graphing this one. So when you go to window, you're going to have several options now. You're going to have your T-min and T-max. That's not really going to matter so much right now. That we can focus in on a little later for when we have intervals. But for our particular question here, we really focused in from -2 to 4. So I'll just change that from -2 to 4. So when you're not given the interval, you can choose it to be whatever you'd like. But when you're given the interval, you'll use those values. Your t-step is what we're going to be counting by. So since we counted by ones, let's start with 1. For our x minimum, it looks like the smallest x value we have is -1. So let's go a little beyond that. Let's maybe go -2. And our largest x value is 8, so maybe we can go a little larger than that, so maybe 9. You can still count by 1 for your x scale. For your y min, it looks like our smallest y value is -1, so again, I like to go a little beyond that, so maybe -2. And for our y max, it looks like our largest is 5, so again, a little beyond, so to 6. Now let's see what our graph looks like. So as you can see, we are seeing that sideways parabola, but it looks a little choppy. Do you notice how the front here isn't as curved as what we drew on ours? The reason for that is because it's only plotting the values when t is -2, -1, 0, 1, 2, 3, and 4. It's not calculating for any of the middle values, like any of the halves or quarters. So if you go to your window and change your step, if you want to have it be a slightly smoother curve, you can change your step. That means what it's calculating, maybe to 0.5 to see what that might look like. So if I graph it at 0.5, we'll probably see that it's a little smoother. And we do. The curve at the front is much more rounded, and if I were to change it to an even smaller step, like maybe 0.1, it would be even smoother. So that's how you can kind of change the look and change your step. Now I'm going to go back to 1 because that's what we started with in ours. And I'm going to go back to graph it. Now, remember we were talking about the flow of how this graph is going, how the particle is moving, and we started at -2. So if I hit my right arrow, I need to hit trace first, so trace, and then it's starting at the t value -2. If I hit my right arrow, notice it moves to the next t value we had, which was -1, and it's giving us the ordered pair 3, 0, which is exactly what we plotted in our graph. And I keep hitting the right arrow, it will take me to my next t value, which was 0, and it will give me my ordered pair. So this shows you the flow or how the particle's moving. And when it gets to the end, it won't go anymore because that's the end of the t's that we had in our table and what we put in our window. Okay, so that's how you can use your calculator to graph these. Let's try another one. Okay, so this is example 2, and we're going to put these two equations into our parametric y equals. So clear out what we have in there and type in what we need. So 1 minus t squared for our first one, and t minus 2 for our second one. Now notice on this one we did have an interval that we need to graph for, so we do need to pay attention to that when we're putting our window in. So we want this from -2 to 2 only. You can change whatever you want your step values to be, again, based on how smooth you want your curve. Maybe this time I'll put them at 0.5 to just get a slightly smoother curve. Now let's look at our x values to see what type of x values we would need. It looks like typically we're going from -3 to 3. So maybe I'll go a little beyond and go from -4 to 4. And same idea for the y values, trying to figure out what our lowest and highest are. So it looks like -4s in our table, so maybe I should go to -5. I just like to have a little bit of extra space on my graph. Okay, so now I have my window, and we should see a sideways parabola again. And we do. Now, again, you can see the flow of this graph, or the direction a particle would be moving in time as you hit trace. So trace will let you move this cursor, and as you hit the arrow to the right, this is starting at -2, and it's giving us the ordered pair -3, -4. It will move. Now, because my step that I chose for my window is now 0.5, it's going to show me at every 0.5 step. So each piece 0.5 will be next. So this is -1.5, and then we'd go -1, and then -0.5, and 0, and +0.5. So it's counting by 0.5s now. And this is showing us the direction the particle would be moving. So now for our last one that I'd like to show you, example 4, we have y equals. I put the sine function in for my x, and my y is cosecant, so that's 1/sine. Now I need to set up my window, and I need to pay attention a bit to this one since it is in terms of radians here. So my lowest value is 0, so I can go ahead and put 0 for my t min, and my t max I can put in as pi/2. Now my step really wouldn't make sense to count by ones because I'm in terms of radians. So maybe since I'm looking at my table here, it looks like maybe I can counting by pi/6. Maybe I can start with that. So second pi/6. So we'll start with that and see what type of picture we get. My x values look like they range from 1 to 0. So maybe I'll go a little beyond and I'll go from -1 to 2. And for my x values, it looks like I'm going from 1 to infinity, really. So maybe I can go from 1 to 3. Or from 0 to 3. Maybe let's do 0 to 3. Okay, so let's see what this graph looks like. Now, it kind of looks like the one we have, but it doesn't really show me that undefined piece. And the reason is because if I hit trace, it's going to start me at, so you notice t equals 0, x equals 0, y doesn't have an answer, and I'm not seeing the cursor. That's because it's undefined. But if I hit 1 to the right, it's really kind of starting the graph at a t value of pi/6, which is 0.5, 2, 3, etc. So that's pretty far away from my axis. If I wanted to see what this graph looked like as it got closer to the axis, I would just need to change my step value. So instead of pi/6, maybe let's make it something really small, like pi/100, just to see what that would look like. And when you do that, you definitely see that curve. And you can see that it's that undefined and then going towards our last value, which was pi/2. So that's this particular curve. Now, there is example 6 in our notes, and example 6 is talking about using the graphing device, which is our calculator. But notice this really doesn't seem like it's a parametric equation. When you have equations that are written in terms of y and you can't solve them for x to graph them like normal, you can use the idea of parametric equations to help you graph the graph to see what it looks like. So all you need to do, and we kind of touched on this when we were talking about revolutions around the axis with area and volume. You want to use the parametric mode, which is, remember, when you have your x1 and y1, and you're going to have your x1 be, now when you type it in your calculator, it's going to be in terms of t, so it'll be t to the fourth minus 3 t to the second. But if I'm really saying that these are y's, then I'm just going to set my y equal to t. Because if I go back and try and put this into Cartesian, remember us doing this process, I know that y is equal to t, so anywhere I have a t in my x equation, it's really just replacing that t with a y, which is what we're trying to solve for in the beginning. So we're trying to see what this graph is. So if you want to do things in terms of y and you're having a hard time graphing it, parametric is the way to go. So turn on your parametric mode and we'll go ahead and see what this looks like. It would be t to the fourth minus 3 t squared. And then for my y1, it would just be t. And let's see what this would look like. So maybe we'll just do a y min of negative 5 to 5. And maybe I'll do negative 10 to 10, just to get our regular standard window. Okay, and if I go ahead and hit graph, now I can see what this picture looks like. And of course, I can adjust my window as needed to see it a little more clearly, but this is the general shape of our graph. So you can use the idea of parametric to help you graph things in terms of another variable. Okay, so at this point in our notes, we're done with the notes for 10.1, which is really just these parametric curves, but I do have an extra little video that I'd like to include in this video, and it's talking about the intersection and collision points. So although this is not part of your notes, please pay attention because you're going to have to use this idea coming up later in the course.
All right, in this short video, we're just going to go through a problem that the video doesn't go through. And this problem does a good job, I think, of explaining the importance of the actual motion of this particle, or in this case, these two particles. So we've got two particles. Suppose the position of the first particle at time t is given by x1 equals 2 cosine t, y1 equals 2 sine t, and the position of a second particle is given by x2 equals 1 sine t, and y2 equals negative 2 plus cosine t. And both of these go from 0 to 2 pi. And so to see what that looks like, we're going to graph it. We want to find the number of intersection points just by graphing. So pulling up our calculator here, we have both of these parametric equations in our x1, y1 and x2, y2. And so let's go to the window and just adjust our t, because we said that our t goes from 0 to 2 pi. Okay, so now that looks about right. And we can see we've got a standard window, so that should work. And this is what our equation's going to look like. Now, to get a better picture of this, this is a standard window. This gives us 10 by 10, but to see what shape these curves actually are, we're going to go to zoom 5. Gives us a square window, so our proportions are correct. Just takes into consideration the fact that this is a rectangular screen. So we can see what this is going to look like. And our intersection points are just, let's see if we can zoom in a little bit. All right. Our intersection points are going to be here and here. That is just where these two curves cross each other. Now that doesn't take the time into consideration. And to talk about the importance of time, we're going to go over to an animation that was created by this website called GeoGebra. All right, so here we have our same two parametric equations in GeoGebra. We can see that the equations look a little bit different because they're in vector form. We're really going to get into vector form in Calculus 3, but don't mind that for now. So we can see our two circles here. our t is from 0 to 2 pi, and now this allows us to see the actual trajectory of this particle. So the direction it is traveling. We can see where our two particles start. And now as time goes forward, we can see that one of them moves in a counterclockwise direction, the other moves in a clockwise direction. And we're approaching our first intersection. And as we're approaching our first intersection, perfect. These two particles collide because they both approach this first intersection at the same exact time, forming a collision. Now, as we continue to travel toward our second intersection, we can see that the blue particle, our first particle, arrives at this second intersection long before the red particle does. Or I'm sorry, long after the red particle. If we move that backwards, we can see the red particle approaches it much, much sooner than the blue particle. And because of that, this second intersection is just an intersection. It's not a collision. A collision occurs when these particles arrive at the same location at the same time. Think about a traffic accident. Plenty of cars arrive at the same place in an intersection, but there's only a collision if they're at the same place at exactly the same time. Now let's see if we can find this point of collision algebraically. We said that a collision occurs when these particles are in the same place at the same time. In the same place means that my x values are equal, so my x1 must equal x2. All right, this gives me my first equation of x1, which is 2 cosine of t, being equal to x2, which is 1 plus sine of t. And the same logic applies for my y values. My y1 must equal my y2 if a collision is to occur, meaning that 2 sine of t is going to equal negative 2 plus cosine of t. And so now I've got two equations. I've sort of got a system of equations. Now this looks a little bit different than our usual system of equations. Generally, if we see two equations, we might see two different variables. But if I look at this first equation, this is a little bit difficult to solve because I need to find out where 2 times the cosine equals 1 plus the sine. However, if I put everything in terms of either cosine or sine, this would be much easier to solve. So we are solving this with the same algebraic principles, but now we're trying to get only cosines or only sines in one of the equations to make them easier to solve. So now we're going to do this by substitution. If I take this first equation, for example, and if I call this sine of t is equal to 2 cosine of t minus 1, just solving for sine of t, then I can plug this sine of t into the second equation. And I can get 2 times 2 cosine of t minus 1 is equal to negative 2 plus cosine of t. All right, let's just simplify this a little bit. I get 4 cosine of t minus 2 equals negative 2 plus cosine of t. All right, so now let's just subtract a cosine from both sides. This leaves me with 3 cosine t equals, and now by adding 2 to both sides, that gives me 0. All right, dividing both sides by 3, I get cosine of t is equal to 0. Now this brings us back to the idea that t is equal to arc cosine of 0 or the inverse cosine of 0, but all that really means is that we want to know for what values of t, remembering that t is between 0 and 2 pi, gives us a cosine of 0. All right, we know cosine of t is 0 at the values t equals pi over 2 and 3 pi over 2. All right, but to confirm that these are both truly collision points, we need to plug them both back into our system of equations. So let's start with pi over 2. Our first equation is 2 cosine of t. So we are confirming that 2 times the cosine of pi over 2 is equal to 1 plus the sine of pi over 2. All right, the cosine of pi over 2 we said was 0. So 2 times 0 is equal to 1 plus the sine of pi over 2 is 1. This will give us 0 is equal to 2. And because that is not a correct statement, the time pi over 2 must not be a collision point. And let's check the other one. It is very possible that we have no collision points, 3 pi over 2. Let's try t equals 3 pi over 2. And testing our two equations here, 2 times cosine 3 pi over 2 should be equal to 1 plus sine of 3 pi over 2. All right, the cosine of 3 pi over 2 is 0, and so 2 times 0 should be equal to 1, plus the sine of 3 pi over 2 is negative 1. Great, 0 equals 0, that is a true statement. Let's test the second equation. 2 sine of t equals negative 2 plus cosine of t. So 2 sine of 3 pi over 2 is equal to negative 2 plus the cosine of 3 pi over 2. Right? Sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0, and we have negative 2 equals negative 2, which is a true statement. Therefore, we get a collision at t equals 3 pi over 2. Just going back to our model here, if we move this bar for t, we can see that the collision occurs at t equals 4.71, which, great, is approximately 3 pi over 2. All right, so we've successfully found the time at which this collision occurs, but we need to know the location where it occurs. So I'm scrolling back up to my original equations here. I know my time that this collision occurs is 3 pi over 2. And because we said that this is a collision, what that means is that both of these particles are going to be at the same place at this time, which means that it does not matter which equation we plug this time into, we should get the same location. So I'm just going to choose the first one. You could try the second to see that your answer is the same. So my x is equal to 2 times the cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0, and so my x is equal to 0. My y is equal to 2 times the sine of 3 pi over 2. Sine of 3 pi over 2 is negative 1, and so my y is equal to negative 2. And so my collision occurs at the point 0, negative 2.